So on this slide, we're taking a look at the specific concept of avoiding dangles, but in general, this is something that applies to digitizing it as a whole. When we're connecting features and trying to ensure that logical consistency is as accurate as possible and maximized, well, there's two different ways that we can do that. One is when we're digitizing a line, um, we can let the vertex be placed anywhere and correct it afterwards manually, and that means knowingly leaving errors in your data set. Or you can use features within the program to ensure that the vertex will be created in the right location and have the correct logical consistency, which, introducing a new term here, is topology. The topology is the science of making logical consistency relationships within data models. So um, there's the everything that we do is manually editing, but there's a little bit of a tweak that we can add to our manual editing to ensure that when we are digitizing line features in particular, that we're going to force the end of a line to jump and attach to another line that's close to it. And how we do that is by taking advantage of something that's known as snap distance or the snap tolerance. And so this is a setting that we can put into our editing session where we tell our GIS to take these different nodes of lines and force them together if they're within that distance. So in this example, we've got these lines A, B, and C that each have end nodes or start nodes, however you want to think about it. A is the one that's being created last, and it ends. And there's a snap distance, which is a radius around the point location, and anything within that radius, if there's a point there, it's going to snap those things together. It's going to pull it and force those two lines to join and become a single line feature. C is outside the snap distance, the tolerance zone, so it does not get pulled in and joined at that node. So if you think about it, employing this snap distance, snap tolerance, sometimes called fuzzy tolerance, in digitizing, if you know that you're going to be working on a linear data set or a polygon data set where um, you don't necessarily want to be zoomed in completely as far as close as you can to get really fine details on these things. If you set your snap distance to a place where you know that you're going to be hitting those nodes to as accurately as you can describe that polygon anyway, here's something that you can use to help make that process a little bit quicker. So we're going to force those polygons, for example, to snap together at the closure of the polygon. We're going to force a road network as we're digitizing it to snap to intersections faster uh, than perhaps we would do manually. So that's what it's for. It's something that you can use to help reduce error, but you have to know and be familiar enough with the tool to understand that you've created the right snap distance for your editing technique and for the needs of your project. So we can set the snap distance or fuzzy tolerance in either screen units or map units. If you set it in screen units, that's going to be a number of pixels on the screen, which is reportedly easier to work with at all scales. If you set it in map units, meaning feet, meters, degrees, inches, whatever the map units are for your data set, reportedly, that can become more difficult to work with when you're zoomed far in or far out from what's normal editing scale or the normal way that people would do it, zoomed in at a certain extent. I can't tell you which one would be the best to use. That's kind of a personal preference. It's something that you will discover for yourself as you're working on digitizing things, if you choose to use the fuzzy tolerance or snap distance settings in the digitization program. We have a couple of options when you are using the snap distance and aspect of digitizing, and you can choose the style of or type of the snap. So when you're putting lines together, for example, and you're calling and enabling the snap distance feature to work, is the line going to snap to the end node end snapping? Is it going to snap right to the line at a 90-degree angle, which is known as edge snapping? Or will it go to the nearest vertex snapping? And so when you set the snapping tolerance or snap distance, then you can also specify which of these versions is going to take precedence in that when the snap occurs. When we're snapping point locations, why would we want to do that? Well, here are a couple of examples. We want to make sure that sewer connections between a house and the city sewer line falls exactly on the edge of the house. So the point snaps to the edge of the polygon that describes the house, which gives us the geographic reality of the sewer line actually exiting from the house and entering the network. Or on the bottom, ensuring that stream gauges that measure stream flow, velocity, river heights, and things like that, that the gauges are actually located on the stream where the instrument is located that makes those measurements. So snapping here for points, makes a lot of sense to take advantage of that if you need to ensure that those geographic spatial relationships are maintained. Your logical consistency then is good. For lines, we make sure that the road ends meet at other roads when there's an intersection, or that they end in space where they're supposed to, or they form a cul-de-sac when they're supposed to, and not be treated as a complete dangle or an overshoot. That's something to be a little bit wary of when you're snapping for a road network or a stream network. But in any event, we use snapping to help in the digitization process to ensure that our segments of rivers, roads, whatever it is, if they connect, that they do connect. They connect in space that we can observe when we're standing right there, and they need to connect in the data sets in order for it to be a really good topological relationship between data set and reality. Polygons, if we're using polygons as we should to describe area, and if those areas connect to one another as they would for property parcels, so there's a legal description of each one of those parcels, and they're done geometrically, and those parcels must join at the corners, and they must share adjacent boundaries between them. So when we have a parcel, a series of private property parcels and commercial parcels, federal land parcels, and all that across space, those, especially the shared boundaries in the intersections between them at the point locations that are describing those parcels, they have to be as accurate as possible. So snapping there when you're digitizing, initially creating a data set or modifying it can be very critical and legally very critical. So we want to avoid little errors that can creep in, and using a snap distance and doing highly accurate, precise, and truthful digitizing in the first place will help eliminate those types of errors that create as the slide is saying here, spurious nooks and kinks, creating areas that don't exist, creating relationships that don't exist is things to avoid in any kind of digitizing process. When polygons are next to each other, as should be kind of obvious, but perhaps not, when you're describing areas, when we use the vector data model, inherent with that is the assumption that when we're describing area, that the area has a boundary. Otherwise, the vector model doesn't work. So we have to have that boundary between, for example, maybe two different land use designations, one agriculture, one urban or commercial or something like that. There aren't overlaps between those land uses that should line up also with property ownership parcels as another vector data set. But we've got to make sure that when we create those polygons in the digitizing process, that we don't introduce things like here, overlaps between them or a gap between them. An overlap says that we've got two land use types going on in the same space, which with categorical information we don't do. And if there's a gap between the polygons, we're saying that that's negative space. Nothing's there, which is usually not true. So we need to try to eliminate these types of topological errors and make sure that the boundary between polygons, when we're creating and modifying polygons, that they share a common, distinct, easily recognizable boundary. When we're creating two polygons next to each other, there's really two methods that we can use for it. One is at the initial phase when we're creating the data set in the first place, we create two polygons, adjacent polygons right then and there. Quite often, we'll have data sets that are created at one point in time and need to be modified by some sort of change that has occurred at a later date in time. So, for example, on the little diagram below, perhaps we have a residential lot in a city that was digitized by the tax assessor's office or the county surveyor at one point in time, and that lot has gone to city council and has been approved to subdivide and to be split into two different pieces of property. And so we need to account for that in our data set, and so you just cut them apart at a later point in time using the editing tools. And those are things that you'll learn how to do in an editing exercise out of the workbook. So to kind of summarize this main introduction to editing in general and ideas of topology, it's a very complex thing. It's something that you want to be very careful about, and as you are creating data sets or modifying them, one warning that I will give you is don't mess with the files in Windows Explorer. So although you may be able to click into a geodatabase and you will see lots of different files in there with different extensions, leave them alone. Do not touch them. Don't do that with any file in ArcGIS. As a matter of fact, don't go into Windows Explorer and get into those different file structures and tamper with them in any way, because you don't know what each of those individual little files is storing unless you're an expert in GIS, and you don't want to take the chance of accidentally deleting something that will make your data set unusable. So what we see normally is going to be the vector representation, point, line, or polygon features depicted across space. Cartographically, we'll make decisions about how to display them, how to label them, things like that. We will be able to access the attribute table, we commonly will not be able to access the underlying data that is necessary for the program to understand the nature of the point, line, and polygon features and all the geometry that goes into them. And we generally don't need to worry about that too much. When we're editing things, we may change their location in space, we may delete segments, we may delete vertexes on a line, for example, to simplify a line or something like that. And the system will take care of updating those other tables of information that are necessary to know those locations, and then to understand the relationships between those locations and the data that we attach to them. But as this slide is saying from our secondary textbook, there's a lot of information about the topology of our vector data sets that we're never going to see and interact with. Okay, so just be aware of that. And again, my major warning would be, do not use the Windows Explorer, File Explorer function to get into these different data files, geodatabases in particular. Leave them alone. One of the really cool features of ArcMap with regard to coordinate systems is that it can edit across coordinate systems. And as the slide's indicating here, your editing is performed in the data frame coordinate system, but the edited coordinates are always saved to the source file coordinate system, no matter what the data frame is set to. So using the example here, we're looking at entering GPS point locations using degrees with the data frame set to geographic coordinates, but they're stored in the file with Universal Transverse Mercator coordinate systems, which is based on meters. So pretty cool to be able to do that. You don't necessarily have to have all of your data in this same coordinate system in order to accomplish digitizing. Now, the best practice, of course, is to have your data in the same coordinate system throughout for a project. But you do have this capability built into ArcMap, which is neat if you can't avoid working in different coordinate systems for some reason, and you need to edit those vector data sets. You can save in the source file coordinate system regardless of what your data frame happens to be set to. So anyway, a neat thing to be aware of. From your textbook authors and from me, here's some really critical ideas. When you're editing, make sure you've got an original copy somewhere, a backup, that you're not editing. In case you make mistakes, in case you corrupt the data, always have a backup copy of things that you're editing. If you edit it, you corrupt it, you lose it, it's gone. So, back up your data. The recommendation is to open up a new map document and then add in only the layers you're going to be working with, edit them, and then save them. Only open the things that you absolutely need to open. The best practice, again, everything in the same coordinate system, and save often when you're working on editing. Words to live by if you're editing, especially that backup idea. And be cautious when you're working with this. It can be, well, editing is very powerful. When you're editing things, you are adding information in or deleting it. And those actions are more or less, well, deleting definitely is a permanent action. It's gone. You're going to have to recreate it again if you delete something, unless you maintain your original data. So again, the critical thing here, always have a backup copy and when you're starting into an editing session.